Okay, so time to start. Very good afternoon, Professor Chandrasekharan, Professor Desiraju, dear colleagues, friends, and students. Should be all right. It's on only. It's on only, right? Just check that. Ivapa, Anthony. Keep it on the table. Keep it on the table. On the other side. Go back in the albums and pick up pictures of him getting interested into the instrumental techniques and the instruments. He wouldn't stop his curiosity. He wouldn't stop his interest to bring it to work to the benefit of the students, to the benefit of the work in the department. Soon after he passed away, there is no denying fact that his legacy and his remembrance must be coming up in some ways towards that. His students, well-wishers, families and friends came together. Professor Rishi Nambudri, IIT Bombay, and Professor H.S.P. Rao, Pondicherry University, took the lead and initiated this endowment fund in the name of Professor S.N. Balasubrahmanyam. With this endowment fund, an institute lecture was initiated, Professor S.N. Balasubrahmanyam Endowment Lecture, beginning from 2022 onwards, and the first one was given by Professor Chandrasekharan, and the second lecture, 2023, was given by Professor Balaram. 2024 was given by Professor Guru Rao, and 2025, fourth in the series, to be given by Professor Desiraju. We are particularly very delighted to receive your concurrence to give this talk in the memory of Professor SNB, so our sincere thanks to you. And we have a program here, so maybe I'm just taking a little bit more time than what might be. So I will welcome Professor Chandrasekharan to give introduction of Professor Desiraju, and then we will be having the lecture of Professor Desiraju on the topic crystal clear engineering complexity, and then we will be having the felicitation and vote of thanks and followed by a high tea. I request all of you to stay over here until high tea and honor Professor SNB's legacy to chemistry at large. Thank you. I now invite Professor Chandrasekharan to come and give an introduction of Professor Desiraju.
Good afternoon. Thank you, Professor Jayaraman. It is indeed a great pleasure for me to be here this afternoon to be able to participate in this fourth Professor S.N. Balasubrahmanyam Endowment Lecture and to introduce the speaker of the day, Professor Gautam Desiraju. Professor Desiraju has been a long-time friend, for about maybe 45 years now since I know him, and a distinguished colleague in the institute, in the solid state and structural chemistry unit of this institute. Actually, Professor Desiraju does not need any introduction at all. In fact, if I have to introduce him and talk about his accomplishments and so on, it will probably take a long time, which I obviously would not like to do. I would like to give the time for him to give his lecture. But I will try to be brief. For those of you who are not familiar, Professor Desiraju got his PhD from the University of Illinois at Urbana-Champaign in the USA. And then he came to this institute and spent about a year as an institute fellow before he took up the position of faculty at the University of Hyderabad in 1979. After spending a number of years there, I think it's about close to 20 years ago, he moved to the Indian Institute of Science to join SSCU. Professor Desiraju is one, probably the most well-cited chemist of this country. His area of expertise spans the area of crystallography, crystal engineering, co-crystals, solid-state chemistry, supramolecular chemistry, and what you would call as supramolecular synthons, and also carbon nanotube-based nanomaterials. There are many, many areas that he has kind of looked at, studied, and published papers. But one thing that I thought I would probably mention, but most of us who are organic chemists here are all familiar with the concept of what we call as retrosynthetic analysis and synthon-based organic synthesis was originally initiated by Professor E.J. Corey many, many years ago. But it was Professor Desiraju who took it up and decided to show the applicability of this approach to solid-state chemistry, crystal engineering, to show as to how the supramolecular synthon could probably do a lot of things for understanding. And therefore, you can make many useful contributions in doing synthesis in solid state. In fact, his approach and his work in the early days caught the imagination of the community of crystallographers all around the world at that time. It made a big impact at that time. And of course, he's been one of those most prolific publishers of chemistry, solid-state chemistry, and supramolecular chemistry, crystallography over the years. And he also served, I think about maybe 12, 13 years ago, served as the president of the International Union of Crystallography. And then he brought the meeting of International Union of Crystallography meeting here in Hyderabad not too long ago, which was a rather successful meeting at that time. He had trained many co-workers, large number of postgraduate students and postdoctorals in this country who are all doing very well in institutions, not only in India, but also abroad. Of course, he has a large number of awards and recognition, which I will not go into, except to mention that he is a recipient of the Humboldt Prize, which is a very prestigious one, as well as the TWAS Prize in chemistry many again years ago, which is considered extremely difficult and very prestigious one those days. Professor Desiraju is one who talks his mind. He really would like to call a spade a spade. That is his very major distinctive quality. In fact, if we have to, and also he is one of the most prolific, excellent, outstanding communicators, not only of science, but also of any other thing that you can talk about under the sun, really. He has published a number of books, quite a few books in that, books on solid-state chemistry, books on crystal engineering, books related to supramolecular synthons and what have you. And of course, he has also written books on science and politics. And also he has, more recently, if you remember right, he published a book on fixing science in India, or fixing Indian science. I have not had the opportunity to read that yet, but I'm told that it's been a rather successful one, well appreciated, and had very good reviews based on what I can hear. To sum up about Professor Desiraju, so good that when he talks, people generally listen. That is Professor Desiraju for you. And I would now like to invite Professor Desiraju to give this fourth Professor S. Balasubrahmanyam Endowment lecture. Gautam, please.
Pleasure. Can you make it a little lower? Is there too much of a hum or something? Yeah. Real pleasure to have been invited to give the S.N. Balasubrahmanyam Memorial Lecture in the Department of Organic Chemistry of the IISc. Thank you, Professor Jayaraman, on behalf of your department for having invited me. Thank you, Professor Chandrasekharan, for these kind words of introduction. I will speak for exactly 1 hour. And since almost all of you belong to this institute, I request that if people have questions, you're always welcome to come to my room and ask me. Because quite onerous to speak in your own institution. It's very rarely done in our profession. Because you go to some other place, you talk all sorts of things. And then even if you say something that you wish you hadn't said, you've gone away and nobody can catch you. But that can't happen here. I have to be very careful what I say. Because I can't run away anywhere from here. It's not common in the academic profession to be asked to speak in your own institution. It is. I don't think I ever gave a scientific talk in University of Hyderabad in the 30 years I was there. It's not common in the profession. Let me put it like that. Now about Professor Balasubrahmanyam. Let me do it from here. Ooh.
Okay, please go. It's not on. It's not on. I'm sorry. It should be on.
Okay. So the physical organic chemistry was mentioned. Now what is this physical organic chemistry? You have something called structure and you have something called property. So the general idea is that if you know the structure of something, you know its property. In those days it used to be called physical organic chemistry. This physical organic chemistry has undergone several avatars in the last 50-60 years. And my own subject, crystal engineering, is a sort of variation of physical organic chemistry, sort of variation. Because it is still concerned with structure and property. The other thing about the structure property business is that chemistry is the only one of the hard sciences where the practitioner actually makes the stuff that he studies. If you take something like astronomy, there is no question of making what you study. Even in large portions of physics and larger portions of biology, you cannot or you do not make what you see. In chemistry, we are always making the things we study. So you cannot divorce the subject of physical organic chemistry from synthesis. In some way or the other, I tell you, all chemistry comes back to synthesis only, because chemistry is about making things, transforming things. So chemists have an unusual power that if you want a particular property, then we say, let us make a particular structure, and we have to make it. That make word is very important. Making. Now in the earlier days of Professor Balasubrahmanyam, generally the feeling was that if you have a particular structure, you will have only one particular property with that. So structure property connection was nice and neat. Similarly, property to structure correlation was also nice and neat. So people made what they wanted to see and then they studied, etc., etc. Now, that's how it was. Subject was like that. The course of this lecture, I hope to tell you that why I said it's a sort of physical organic chemistry, this crystal engineering, is that this connection between structure and property is not as neat and smooth as it was in the old days. Today, same structure can have different properties. Same property can have different structures. So you see, this is where the word complex comes in. In the old days, it was a simple connection. Today, structure property has got a complex connection. And that's why I said it's a sort of thing. Now, many of the students of Professor Balasubrahmanyam are here or they are listening elsewhere. My own PhD supervisor was also a physical organic chemist. Not many know that I was a student. And it's better it's like that. People should not know who your supervisor is. Because today I see too many cases of people who are introduced as so-and-so student, so-and-so's postdoc. Worse than that is if the fellow is introduced and said, you know his student is the great so-and-so. That also I have seen. When the student has become, so generally the student-teacher relationship should be kept private. It's a private professional relationship. So many of my students that way have been mavericks. They don't go for the usual thing. And so both of them, first and last, little bit unusual. Talking about Tejinder, I'll come to this guy, Ritesh Dubey. Now, Tejinder, Ritesh and I wrote a thing in annual review of physical chemistry. Now, this pointer is green. This one, annual review of physical chemistry. So I guess it is physical chemistry review. Now, the PhD work that Ritesh did, however, I'll talk about this towards the end of my talk. Strategy and methodology in the synthesis of multi-component molecular solids. Synthesis. He made some weird organic compounds which would form these higher co-crystals. He was trained as an organic chemist when he came here. And so this is organic chemistry. Then he went and did some postdoc somewhere and all. He tried to start searching for jobs. So sarkari naukri nahi mila isko. So here and there he tried all over the place. So then he said, no sir, wherever I go, somebody who doesn't like you is sitting in the selection committee. So I said, okay, go to some place where these people are not sitting there. So he said, what kind of place is that? I said, go to a private university. Sir, no, I can't. I want sarkari naukri. I said, no, these places are good here. I know some of them. Today he is in a place called UPS, University of Tomorrow it's called. It's really a University of Tomorrow. It's a corporate culture where financial decisions are taken on the basis of a WhatsApp. And it is based on the honor system. If you cheat on that, you lose your job. Okay. The selection is also easy. The firing is also easy. See, what is the difference between putting your money in the post office and going to the share market? Like that. You fellows have to learn how. See, today Ritesh tells me, he said, sir, the best thing you told me is to go to a private university. I'm so glad I don't have a sarkari naukri. Because now he's getting papers in our standard crystal engineering journals. Lastly, this polyhedron is a journal of inorganic chemistry. And Ritesh has joined me in the editorial board of this. And he and I are taking decisions on submissions made to the journal. And so now what is this fellow? Is he physical chemist, organic chemist, inorganic? What is he? Doesn't matter. Because chemistry is a very unitary subject. There is no difference between organic, inorganic, physical, nothing. Zero. Basically same thing. All over chemistry you find physical, organic, synthetic, whatever. Whatever you get fastest is better than what is best. Kinetics always trumps thermodynamics in chemistry. Whatever you get fast is better than what you think is the best somewhere. It's also true about relations between countries, foreign affairs, state of India today, everything. This is the dictum because time scales are getting very short. You can't go on waiting until you get the best result. That will never come. Okay, so that is Ritesh. And then this is that book, Fixing Science in India. Yes, fixing. You only fix something that's broken. Socio-economic prescription. Prescription means what? When you go to a doctor. Healthy people don't go to doctors. So the book is there outside in case some of you all want to buy it. So this is my latest student. He's not even a scientist. He's a lawyer. And he is only 26 years old. Okay. He knows more than half this audience why you need dysprosium in a neodymium based magnet. He knows why when China has a multi-step synthesis of an API, it will sometimes sell the product of a reaction cheaper than the starting material. He knows the reason for that. Normally you would think, no, starting material should be cheaper than the product. No, he knows why sometimes the Chinese do this to us. So you see, you don't even have to formally go through a chemistry degree or a science degree to be able to talk about these things. And this green book, Supply Chains in a World at War. War. We are a nation at war. And today I will tell you, Professor Chandrasekhar will appreciate, a synthetic target, it's a target, Chandra. The synthetic chemist is waging a war to go and hit that target. He wants it. So any synthesis that you do is a ladai. You have to go there and get it. Why do you go and make this fancy molecule or fancy crystal or whatever it is? So the whole atmosphere now is research itself at a certain level becomes like a kind of war. So anyway, this is Mr. Bhattacharya. And let us go to some real science. So I have talked about, this is my Manasika Guru, Professor Alexander Kitagorodsky, who told us that molecular crystals are close packed. But unlike your inorganic solids, extended solids, where you have round things, atoms and things, where they are all in hexagonal and cubic symmetry, these molecular crystals go down into monoclinic symmetry. So that's what he told us. Much of his work was done in the 40s when he was less than 30 years old. So he gave us the basic model. But till now there is still no chemistry. There's geometry maybe. There's a bit of topology, maybe a little physics, but no chemistry as yet. What is this close packing and all that? Crystallography, space groups, nothing. So this is the point where I came into this field. And I said Kitagorodsky is broadly correct, but the devil is in the details. Now look at this. This is chloroform and that is acetone. Now what is that H dot 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 O? It looks like a hydrogen bond, doesn't it? Of course you will tell me the hydrogen is very activated because of those chlorines. Yes, but it is somewhat acidic, carbon acid. So then the question is something like this a hydrogen bond or not? Can you call it hydrogen bond? Can you call it bond? So this is what got my interest in these kinds of things. And the early 90s or so, a coffee ellide. Coffee idi alli. So, no, I'll help myself. So, see, look at this. According to people like Kitagorodsky, when you take a carboxylic acid, this is benzoic acid. This is very well known. Benzoic acid dimer, hydrogen bond, the strong hydrogen bond everybody knows. Now, according to Kitagorodsky, this thing should be a center of inversion, symmetry center in the crystal. And then we had a look at this particular creature, 3,5-dinitro cinnamic acid. Then I noticed something very peculiar. You still had this dimer, but this dimer was located on a two-fold axis of symmetry and not a center of symmetry. So center means like this, like this. This is center of symmetry. Two-fold axis is like this. So it got bent like this. So then the fellow may say, oh yeah, it's still the same hydrogen bond. Why are you quibbling so much about center of symmetry and two-fold? The thing is, there is something in this rest of the structure that is pulling these things down and not keeping it like this. Something is pulling it down. And then when you look at the structure itself, it's not hard to find out what that something is. These are these weak hydrogen bonds. All this junk. The whole thing is full of weak hydrogen bonds. And if you look at the molecule now, you will see that every hydrogen here is ortho or para to an electron withdrawing group. It's highly activated, those hydrogens. So you don't see this in 2,4 dinitrosidamic acid where it's not like that, but only in 3,5. So this is an odd creature. And it forms a pattern. Some youngster, please help me with opening this. So these are all crazy structures. So we started looking at a number of them. And Woodward used to drink whiskey like this. I am drinking only coffee. His seminars apparently would start at 7 in the evening or something and go on till 3 in the morning when all the people used to droop off. So that's what led to this crystal engineering idea that there are 3 aspects to crystal engineering: the interactions themselves, and then the design, and then the properties. So this definition which I gave long ago still has stood the test of time. Interactions, design, properties. So if you understand these weak interactions, you can design a structure. You can go out above the Kitagarodsky model and get to the fine details. Yes, they are close packed, but only in a way. Every time you have an interaction, there is some deviation from close packing. It is the some deviation that brings the whole chemistry into the picture. Because these interactions are nothing but chemistry. There is no more physics, no more geometry, no more topology, nothing. It's only chemistry. So many things. After some time, one textbook also came. So the 1989 book has stood the test of time, is now out of print and all that. So main thing is core issue, crystal structures cannot be predicted from molecular structure. This is the thing, as I said, what is a molecule? You have to know that first. From molecule to crystal, is there a one-to-one correspondence between a molecular structure and a crystal structure? What characterizes a crystal structure? Is it the structure or is it the property? It's very important because, as I told you earlier, this new physical organic chemistry, structure and property are not directly correlated, not so easily. And therefore we get into what is a complex system. A molecular crystal is a complex system, as opposed to things like MOFs, which are simple systems. I'll come to that a little bit towards the end. So the behavior of a functional group in a molecule depends on the nature and positioning of all the other functional groups, with the added complication that the hydrocarbon part of the molecule is also a functional group. So the entire molecule is like something that's interacting with all the other molecules. So out of this you have to pull out something that is essential, the core of the crystal structure. You have to pull something out. Now look at this. This fellow is Kumar. who is now a professor in IIT Kharagpur of long-standing seniority. Thing on the left is ordinary hydrogen bonding. Nobody has a problem with that. Now this is the same topology based on weak hydrogen bonding. Kumar did this structure. So now look, we are going to reframe synthesis so that the synthetic target is no more the molecule, but it is the supramolecular part. This is the synthetic target. And this is actually equivalent to this. So when you make a molecule using Corey's retrosynthetic model, you go for a molecular feature and then you do what is called disconnection. So you break the molecule into parts that can be recombined back using a synthesis. When we make a crystal, we disconnect the supramolecular part. That's what we do. And this then is the model of the supramolecular synthon. Now, we can skip this, but since this is a department of organic chemistry, this is Willstater's synthesis of tropinone. Chandra, you may be interested to know that several people who were postdocs with you in the Corey years when the retrosynthetic thing, I have asked them, what do you consider to be some of the most famous synthetic routes in history? Most people mention Willstater's synthesis of tropinone. Now what is this? Why am I still talking about this in an era when this whole way of doing synthesis is not there anymore? I mean, let's take a very simple example. In 10th class exam it will come. How do you make para-nitroaniline from aniline? 10th class it is. When I was there it would have been in BSc, but now it has come to 10th class, this question. So if you take aniline and nitrate, you will get a black goop. We know that. It won't stand to the nitrating mixture. So what do? You protect it, acetylate it, make it acetanilide, nitrate that, and then deprotect. So anybody can think of these three reactions: protect, nitrate, deprotect. So thinking of three reactions in a forward direction, any of us can do. Now Willstater thought about 16 reactions, starting from suberone to tropinone. Tropine last stage we'll forget, it's simple reduction. So the fellow was able to think of 16 reactions in the forward direction. That's, no human being can do it, but Willstater was very much a human being. Just imagine thinking of all these things. He actually did this. So in terms of sheer intellectuality, it is, that's why I'm talking about it so many centuries after it was done. But just 10 years after Willstater came this simple thing from Robinson. What Robinson did was entirely different. He took tropinone, this is tropinone, and then he did a disconnection. And then you can see the elements of tropinone in succinic dialdehyde, methylamine, and acetone dicarboxylic acid. You can see the whole molecule here through a simple condensation reaction. That is retrosynthesis. I think that's clear enough. Now let's go a little faster. We'll go through some of this fast. So see, this is one of the synthons, iodo-nitro. So you can see para-iodo-nitrobenzene forms this nitrosynthon. But you can get the same structure by taking para-dinitrobenzene and para-diiodobenzene. So a single molecule, one molecule crystal has the same crystal structure as a two molecule crystal. So different molecules can have the same structure. See, already I am going away from that old style. Then we can go one step further. So you can take diiodobenzene and then I can add this amide here, because I know amides and amides form another nice synthon here. This is red. Then I take diiodobenzene para-nitrobenzamide Dinitrobenzene para-iodobenzamide. So I can just switch the functional groups around. So many of these different binaries have same crystal structure again. All of them have if you define a molecular target in terms of a molecular structure, a crystal target is defined in terms of topology. I want a ribbon, I want a sheet. Because ribbon has one property, sheet has a different property, like that, like that. Put the third component. So I take my diiodobenzene, I put my para-nitrobenzamide, and then I put oxalic acid because I know that these acids and amides also like to club. Now why do you get these structures at all? In all these structures, please remember there is a hierarchy of interactions. So the green is stronger than the red synthon, which is stronger than the yellow synthon. But the yellow is not so weak that it doesn't enter the picture also. It is strong enough that it enters the picture. It is weak enough that it doesn't disturb the red and the green. So you have to understand these interactions and grade them before you can start putting many things, many molecules in one crystal. Now why is this an important problem in crystal engineering? Because crystallization is always a purifying technique. You take brine or you take molasses, you get a pure crystal out of it. Crystallization is an excluding phenomenon. It throws everything out because the tendency to form a single component crystal is very high. So when I am trying to put 2 and 3 and all into the same crystal, I am fighting against something. That is the synthesis part. Trying to make these kinds of things that become more and more difficult. So like that I can go on and on. Okay, now strategy, methodology. Strategy is what I have been talking about till now. What you do, what you want. Methodology is how you do it. I talked about war, no? Why synthesis like war? You have this in wars. There is a strategic component, there is a methodological component. For example, strategy would be said by Modi saying go and attack that Bahawalpur, that mosque. Methodology is how you go and do it. Shall I attack in Gujarat side, Rajasthan side? Shall I attack by aeroplane or shall I attack by boots on the ground? And just like in world affairs, diplomatic affairs, even in chemical synthesis, the moment you start mixing strategy and methodology, you get into trouble. Politicians decide strategy, the military decides methodology. And the politician starts telling the fellow, no, you don't attack in, Gujarat, you attack in Rajasthan or something. Strategic fellow is talking about methodology, which is not good. I'd like to come, if I had come to the end of the talk, I would like to see whether there are certain aspects of strategy where methodology is essential. That without that particular methodology, that strategy itself is impossible. But I don't think that crystal engineering has yet come to that stage when there is some small overlap. But as far as I am concerned right now, strategy and methodology are a little different. So methodology is really these interactions. We don't have much time to talk about interactions. This is hydrogen bond. And this was the second big issue that I got into in the course of my research. See, in hydrogen bonding, we were imprisoned by an old definition given by Pauling, who said that hydrogen bonds have to be strong. So the moment something was not strong, they said it's not a hydrogen bond. So the things in the first row are all like that, strong. Then in the second row, OH pi, the donor is strong and the acceptor pi is weak. NH pi also, CHO, donor is weak, acceptor is strong. Then this below is not a type, is really osmium. OSH, this H is protic, it's not hydridic. And it is a hydrogen bond, it's weak. CHNI, donor is weak, acceptor is weak. CH pi, donor is weak, acceptor is weak. All these things have certain properties that look like strong hydrogen bonds. Some things, not all. Professor Arundan is here. He chaired a committee where I was a member on definition of the hydrogen bond. That paper went to some 23 referees or something. Nobody knows still what a hydrogen bond is. Nobody knows. I'll tell you that. Not me anyway. So, this fellow Steiner was a young postdoc with Wolfram Sanger, who was experienced hand in hydrogen bonding. So he and I got together and we wrote this famous book, now famous book, The Weak Hydrogen Bond in Structural Chemistry and Biology. So we said that two structural moieties, even one or both of them are of moderate to low electronegativity. So the thing is that now we are getting more into property and less into structure. In all these kinds of interactions, what it does is more important than what it is. The moment you try to start giving it a classification and a name and saying it should be this and it should be that, you get into trouble. And Arunan and I know how much trouble we got into in this issue. It is, in complex systems, it is often easier to go for property rather than for structure. This is not a comfortable idea for Westerners to take, let me tell you. It is very comfortable for people in this country to take these kinds of ideas on board. Because Bharat itself is, I think, one of the best examples of a complex system. It's not a simple system. So much diversity in this place, and yet it's all the same. Which is why my transit from crystal engineering to writing some of these books was not a natural one. We are studying the same sort of thing. So this is Thomas. He is also a maverick. Shortly after writing this book, he quit research altogether. And he is now quite a wealthy man of doing all things, translating German and English patents and books and papers into the other language. He is very fluent in both languages. So he said all these academics thing are all useless. He says, I'm making more money by doing these translations. Especially the patents and all these companies pay him a lot of money, because in the patents the exact wording and all is very important. So you see, there are many things you people can do. Something IISc, PhD, I will go to Columbia, postdoc, after that I will get a job, I will sleep. After 20 years I will export my son to USA so that he can give me my pension. Not required to do all these things. So many things you can do. He is a very good researcher. He had 170 papers when he just quit cold turkey. He said that's enough. So this was, he is smiling, you know. He never used to smile when he wrote the book. This is him in his new career. Yeah. This is that whole hydrogen bond thing. You can have different extremities, very strong electrostatic van der Waals. This is one very borderline region. Is it really a hydrogen bond or not? Can go on fighting. Because you are trying to give something a name when it doesn't have a name, anamika. You don't know what it is, I am telling you. Whole life I have spent doing hydrogen bond, I can't tell you what it is. Halogen bond, see the next thing. We try to become too smart and say just like hydrogen is electrophilic, halogen also is electrophilic. So we wrote this article, Accounts of Chemical Research, famous journal. When I look at this paper now after that, what is this nonsense title, like hydrogen bonds yet different? I am not even telling you what is a hydrogen bond, and I am telling you halogen bonds looks like it, but it is not like it. I am reminded of one name in the famous Lalita Sahasranama, Drishya Rahita. You are trying to go and search for something and then you find that it is not there also. Trying to say what is a hydrogen bond, at the end of the day I don't even know what it is, but it's there, it does things. We know certainly it does things, because if its hydrogen bond is not there, there won't be life in the form that we know it today. Certainly it does things, but we don't know what it is. Very important to know this. And see, people who think in a reductionist way will not appreciate this, but people who think in a non-reductionist way will find nothing wrong in this. We wrote a definition also. The only thing I told all these guys, whatever we write, please make it general enough so that tomorrow if somebody comes up with some nice experimental finding, it will fit in this definition. Let us not make the same mistake that Pauling made by saying that this bond is strong, this bond is weak and all that. Those are all very stupid things to say about these interactions. Yes, Pauling was stupid in saying hydrogen bonds should be strong. He may have felt he is right at that time, but scientist has to say something which may be true for some time to come. You can't just say the world ends today, you know. Now we are going higher. Already the synthesis is difficult. This is not a photograph taken from Google or something. It's taken by one of my associates who actually went to this place. Believe it or not, CSIR has a lab in this area where they are studying cold desert, I believe. Some plants they are studying. CSIR is actually doing something. This book has a lot to say about CSIR. We can't get into that now. This is Sindhu. In the portions where it flows through India. Quite a bit of Sindhu goes through India, you know. And recently I have written an article in Organizer on the fact that the Sindhu belongs to 3 countries. Afghanistan, Pakistan and India. And none of the borders between these 3 countries are likely to be permanent. But that river is permanent. It has always been there, it will always be there. So we must realize sometimes what is permanent and what is impermanent. This Prasad, he brought this up. See, I have always been thinking about crystal engineering and the fact that putting different molecules together. Apparently I showed this slide in the last time I spoke in this department 40 years ago. I have forgotten this talk also. Prasad brought it out for me. So he said, you use the word crystal engineering. Yes, I used the word, although I don't think I knew what it meant. I think it was 1984 or something. But still the idea of bringing different molecules together. And the next thing is this co-crystals, putting more molecules together. The first big application of crystal engineering was done by this gentleman, Mike Zavarotko. He is now in the University of Limerick in the Republic of Ireland. So he took from my synthon model and then he said, let us put 2 different molecules together, one which is a drug, medicine, and the other one which is a facilitator to make the drug more soluble. So some of these drugs are insoluble. So when you take the tablet, it won't dissolve. So you put the second molecule which makes it soluble, and there is something called kinetic solubility, so that immediately when you take it within the first half an hour or so, because of this kinetic solubility, this co-former will make the drug soluble briefly. But that's briefly enough that it can go through the esophagus into the stomach. Then, so all these people made many of these co-crystals. They are called pharmaceutical co-crystals. And they are using again the synthon model because he called them heterosyntons because 2 different molecules are coming together. One is the drug and one is the co-former. This last one is important, Entresto. It's the first big co-crystal which is being sold in the US market, which is very, very big. They have recognized the fact that a co-crystal, a pharmaceutical co-crystal is a separate drug which is entitled to separate patent. It's got nothing to do with the original drug. This was a very, very big victory for all of us. And then my own group here in the institute, then we started feeling that in addition to solubility, there is something called permeability. This whole thing up to here is aqueous medium. When it goes through the gut and has to enter the small intestine, then it has to go through this aqueous lipid barrier. So the thing has to have a mixture of hydrophobic and hydrophilic characters so that it is aqueous enough to be soluble and lipid enough to go through the membrane. So that is called permeability. So how do we adjust this solubility and permeability? Again through this co-crystal business. So the idea is different portions of the drug have different properties. Then this is again back to the old problem, classic problem. Higher co-crystals. Okay, we've made co-crystals of 1 and 2 components. Now, these two fellows, I talked about Ritesh, this is Niaz, and we had this ternary co-crystal, tetramethylpyrazine, and this is some polynuclear aromatic hydrocarbon which stacks. Then there is a hydrogen bonding to this 2-methyl resorcinol. And we all noticed that the 2 hydroxy groups in 2-methyl resorcinol, they are non-equivalent. One is hydrogen bonded to nitrogen, the other one to oxygen. So they are non-equivalent. Chemically they are different. Okay. Then we can exploit this difference. How? Once they are different, then we can put the 4th component. And once again, it's a question of calibrating the interactions. The 4th should be strong enough that it comes in, but not so strong that it destroys the existing ternary and then forms something else new and unpredictable. So it has to be a very gentle graded addition of interactions. So we actually got 4 in one crystal, and we not got 1, we got about 30-35 quaternary co-crystals where they are all stoichiometric. A few groups have made 1 or 2 after that, but still nobody can catch us in the terms of the number of quaternary, stoichiometric quaternaries that we made. This is quite tough, I can tell you. So schematically this is illustrated, this is a binary. So when the binary can be of one type where A and B are equivalent, then nothing you can do, synthetic dead end. But if the 2 are non-equivalent, then you can tease it with C, then again you may get a dead end, but you may not. So this can also lead to C1, C2, then we can put D and we can get to D. So at each stage, you can make it progress. So this is supramolecular synthesis. This is real supramolecular synthesis. One more example, another big example of what complex systems are capable of. You see these crystals, molecular crystals, they can be bent, twisted. Unlike a metal which can be bent, twisted isotropically in all directions, these things can only be bent, twisted in certain directions. On these various kinds of molecular crystals that have so many different properties, plastic, elastic, super elastic, brittle, when does a crystal break, when can it be bent, when can it spring back? If the restoring forces are strong enough, it will become elastic. And all this on the basis of the interactions. And shortly after that, so many reviews appeared in top journals on this same topic. So again, once again, these are crystals whose properties are completely dependent on the fact that we are dealing with a complex system. It cannot happen in a simple system. This is a very nice example which Shubhankar did. Same structure, different property. There is a bromo and a chloro analog with isomorphous, same structure, A, B, C, alpha, beta, everything same. One is elastic, one is plastic. That's simply because the BRO interaction is of weaker strength, stronger than the CLO interaction. It is just that small difference in the interactions that changes the property. So same structure can give different properties. Again a feature of complex system. So 3 generations of crystal engineering. The first, molecular structure to interactions, simple. Then now we are thinking retro. Crystal structure going back to interactions, that is synthon. Third is property engineering rather than crystal engineering. So you search for a property and then say what crystal or crystals can give that property. Property comes then higher than structure. So you can see how much the idea of physical organic chemistry has changed. And then of course the first Gautam conference in crystal engineering, after a long and hard battle with the GRC people, Robin Rogers and myself succeeded in getting a GRC called crystal engineering. This was a mighty struggle because they gave us the project easy enough, but the title of the project was like a long abstract. GRC in crystal engineering including MOFs but excluding COFs, plus this plus that, including bromo but excluding chloro. So I told Robin, we will not accept this proposal. Either you give us GRC in crystal engineering or nothing at all. We don't want anything. No, you don't want MOFs. No, we don't want MOFs. Subsequently, MOFs I think got a GRC. The problem was there was a GRC already in something called physical organic chemistry. So they said, what happens to all those people? I said they can do whatever they like, but because that is there doesn't mean we can't be there. Free and frank. Chandra just said that I speak my mind, spade a spade. Spade a spade even to GRC. Don't want means don't want. No, they said okay, we'll take. Fine, we'll come. So this was the first one in 2010, it's going strong. And then we wrote an article, this future. You can always write articles on the future because nobody knows what's going to happen in the future. But still, I will emphasize, with all this confusion with MOFs now. MOFs are simple systems because the nodes and the node connectors are very strong. So the structures are completely predictable. So the attention immediately goes to the properties. There is nothing great in making MOFs. Thousands and thousands of papers only from China. The main thing is to get the property there of the porous solid. So I view this, and many crystal engineering people view this as MOFs as one of the things that can be done. But pharma, I have spoke about thermosalient actuators, the soft crystals. I have not had a chance to really talk about this. But we've given a wish list here. Just like Lippard's wish list for chemistry, Silent Revolution, which he wrote 25 years ago. So we've given a wish list for crystal engineering, people can look it up. So these are all fellows who showed up. Some of them in the Hyderabad conference that I've had the pleasure to work with. Only some of them are here, some of them in the conference but didn't show up for the photo. So all are rogues. So, okay, they all did well. So number of things, memories over the years, too many memories, or mostly nice ones. And I've led a colorful life. Now I want to ask you something about this. When you see this picture, do you see a man's face or do you see vegetables, fruits and flowers? How many saw the man's face first? Hey? Oh, good. Good. That means you are thinking supramolecular. Anybody who saw the fruit and vegetable and flower first is still thinking reductionist molecular. So where did I put that picture, the Himalaya picture? Because it's all very damn difficult stuff to do all this. Now, once you go there, you are alone, but you are not lonely. Then you want to know what to do next. You know? So what did I do next? Noting the similarities, so many similarities between this holism, non-reductionism. Whole is greater than sum of the parts. I started thinking more about, partly because of COVID and I had to sit at home and do nothing. So this Bharat book was the first of this series, where actually I discuss India, Bharat as a complex system. India is a simple system, Bharat is a complex system. So anybody who goes on saying India, India, India is still thinking old way, American way. Anybody who is saying Bharat, Bharat, Bharat is thinking the new way, which is actually our very old way. So, some of these books are there outside. This blue book, white book, red and green are not there. So, Professor Joshi was formerly education minister of the country and all, but he is the PhD student of the great Kedareshwar Banerjee of Allahabad University, who wrote the original paper on direct methods in 1930-31, which Karl and Hauptmann referred to 50 years later in their Nobel lecture. Because when Banerjee wrote his paper in Nature, crystal structures used to be determined in some very dirty way called trial and error. You actually put some structure and then saw if the reflections fitted. That was no method at all. And Banerjee showed that the amplitude or the intensity of a reflection had something to do with the phase. A very original idea and brilliant idea. And then Joshi is the PhD student of Banerjee. He is not my Manasika Guru, I talk to him very often. Because he goes on talking about this, he wrote a beautiful foreword for the delimitation book. And he also said that this blue book, which is for sale outside, he said everybody must read. But he also said, is everybody intelligent enough to read this book? Well, what can I do, Professor Joshi? I mean, I wrote the book, but it's up to people to figure out the things for themselves in the end. The final 5 nimisham. 5 minutes. So I am still within time. So I've got into this IKS, Indian Knowledge Systems. At a time when nobody is getting grant from ANRF, I got this big grant from these fellows, ministry, to write 2 textbooks on IKS, Indian Knowledge Systems. One for class 11 and one for first year UG, which will be distributed all over India. So I told them I will write, but I am not going to write a book with all some ancient rishis and orange robes and Pushpak Viman and Gomatra and all that. That I am not going to write. I am going to write 2 books for the modern person like all you guys living in metro cities, interested more in motorbikes, pizzas, girlfriends, boyfriends. You tell them all these things, old stuff for Gomutra, and they will say, go away, we don't, nonsense. So I said, I'm allowed to write the whole book in English without any Sanskrit things coming in the middle, and all this Vishwamitra Vasishta and all, if I'm allowed to do like that. If I'm allowed not to overtly bring in religion into this whole business, because IKS goes above religion. When I said I'll write, they said, no, Professor Desiraju, no, whatever you want. When government wants you to do something, I figured out they must be needing this thing pretty bad. When they want you, then they said, okay, we'll, please. But they gave us a very strict deadline. So we've almost finished book 1. The young man here, Mr. Panda, who is well trained in Brihat. So he is helping me to write along with my other co-author Dikit Bhattacharya. See, we have a regular basis for this. I'm not talking bunkum. In India, we knew that zinc was a metal 300-400 years before anybody in Europe knew it was a metal. Zinc is very unusual because the difference between the melting point and the boiling point is so small that when you try to smelt it like other metals, the zinc vapor simply gets oxidized and goes back to zinc oxide. So we discovered this technique of downward distillation. I mean, you're not able to do all this just by trial and error, random and all. They knew very well what was happening. And they did it in a very clever way because they found out very easy to make brass, but not so easy to get zinc. So through that they deduced and then got this whole thing. And the very last example, what is the first 3 chapters? These are the first 4 chapters of the first book. What is Indian? what is knowledge, what is systems, what is IKS, what is Indian itself, I wrote the chapter. What is knowledge, I think Anshu here wrote that chapter. And what is systems, Dikit wrote that. So the systems is all this layering, what I showed you in those quaternary co-crystals and all, bringing interactions of different types. Knowledge is this 14 streams of knowledge. Chaturdasha Vidyasthana. So many things, 4 Vedas, some Puranas, epics, this, that, Jyotish. Each of those is a different stream of knowledge. So we take all the streams of knowledge and combine them into a holistic unity. And since I have some knowledge and experience of Carnatic music, yes please, Yaru? Somebody said something? I have some knowledge of Carnatic music. I started looking at this fellow here, Muthuswami Dikshitar. He intrigued me a little bit in the context of IKS. And he wrote about 480 songs, and some of which are widely sung and practiced today. Then I started looking, I've been trained, I should tell you, in Carnatic music, but I stopped completely in the early 90s when the synth-on work became too intensive. I figured out I couldn't do two things equally well. Otherwise I'll do both things badly if I try. So I stopped music completely, I just kept listening. It never went out of my head. Then I found a group of rare songs that this fellow wrote. They were on a particular goddess called Abhayamba. And there are 8 of them set in the 8 Sanskrit cases, nominative, accusative, etc. There was a invocatory song and there is a concluding song. I have been hearing Carnatic music concerts for 55 years. I can tell you I have not heard a single one of these 10 songs even once in a live concert. So there's something odd about these songs that nobody wanted to touch. They are like that. They reminded me immediately of 3,5-dinitrosinamic acid. Something that looks so odd and so funny that people, they're very difficult to sing for a start. That doesn't matter. Many difficult things can be done. Why did people avoid these things completely? I started asking, Often in science, it's not providing the right answer, but asking the right question. Most people don't know how to ask the question. Then I started looking at it a little bit more and then I was astounded. Because in these 10 songs, he has encapsulated the essential idea of Indian knowledge and systems. And I wrote an article on that in a journal called E-Samskriti. Not all of you may be interested in Carnatic music or IKS, but there are a few copies here for those who may be interested. Muthuswami Dikshitar was an epitome of Indian knowledge systems. You don't need to know a single note of music to be able to read this article. Not a single note, is not required. So it's nothing particularly musical about it, but it is the way in which he has layered these 14 Vidyasthanas in these compositions, the lyrics especially. You can view it as a simple collection of names to the goddess. Otherwise you can go higher level to Sri Vidya. After that you can go to Tantric. There are meanings at different levels based on the experience of this. This whole IKS is very contextual. It's not, whereas Western knowledge systems are not contextual. The observer and the observed stand apart. In our system, they are all together. There is no difference after some time between the observer and what is observed. That is the difference. And I'll give the example of this last one, very last example. This Mangalakriti in this group, very strange song, because it is written in 3 languages. It's a kind of rare composition called Manipravalam. And the Pallavi, the opening line, Sri Abhayamba, that is Sanskrit. Ninnu Chintinchina Variki, Telugu. Those who are contemplating you. Inda Kavala Yellam Tirum Amma, Tamil. So he has put 3 languages in a single line. Now this Manipravalam technique, not there in Sanskrit poetry. Kalidasa and all have not used it. It is there in early Tamil poetry. And the earliest Manipravalams were between Tamil and Malayalam. Then they did something with Tamil and Kannada, then Malayalam and Kannada. These 3 languages are closely related actually. Telugu stands a little bit different. The grammar is a bit different. Then finally Telugu came. Now I don't know what you thought. But when I looked at this Manipravalam, I've heard it sometimes in recording. It's not performed also. I don't know what you thought. I thought this is my ternary co-crystal. It is just as difficult to make those ternary co-crystals that it is to write this thing in that smooth way. It flows very nicely when you think it. Sri Abhayamba, Innu Chintinchana Variki, Ivala Kavale Yellam Tirum Amma. Goes nice. Very auspicious ragam, Sri Ragam. So even if you are committing any musical sin, that Sri Ragam will wash it all away. So, now I'll meet this guy one day, I'll ask him, how come you never did a quaternary co-crystal? I got 34 of them. Can you write a Manipravalam in 4 languages? See, it's the same thing, you know what you're doing. And I think I know little more chemistry than I know Carnatic music. At the present moment of time, I can say that the chemistry co-crystal is a bit more difficult than writing this 3 language music. But I don't know how it may change tomorrow. For example, this AI business, last. This AI has turned everything upside down. Will it make the whole subject of crystal engineering redundant? We've written a paper, Mr. Bhattacharya and myself, in a journal called Innovation. Is the data deluge actually killing our imaginative ability itself? That our imaginative processes are getting cut because of this AI. Then I did a simple experiment again. If you take a piece of Western music, however great it may be, I'll cheat a little bit and take the music of Johann Sebastian Bach, which is particularly digital in its nature. So if I give a few things and give it to AI, it will produce a composition that sounds pretty much like Bach. I don't know enough of classical Western music, but to my untrained ear in that system, it sounds pretty much like Bach. AI can do that today. I did a similar experiment with this chap, with a collaborator in, where is he? In Cleveland, Ohio. We took the lyrics of all his 480 songs and we dumped it into that and said synthesize something and produce some lyrics. Even stupid people will realize that that is not a Dikshiter composition. So there is something, maybe AI will improve in the future, that it will be able to reproduce a Dikshiter composition, but right now he is ahead of AI. And if you take some of the other great composers in Carnatic music, they don't stand up to this test. You can make something which looks reasonably like this. So there is some added extra in this particular fellow's compositions that defies our present thinking, which is why we are including him in the IKS textbook. We have taken 5-6 people who exemplify IKS, Kalam, Dharampal, Sumati Murarji. We have taken Sarojini Naidu, and Dikshit. So we have taken some 5 people who in our opinion exemplify IKS. And in the end, all I can say is that what I have written in the book also, do not be afraid. Abhayamba dispels fear. These are the lyrics of one of those kritis in Todi. And we come to the end. Once again, this is not a photo that is downloaded from Google. It was actually taken by the Vice Chancellor of UPS University, who is an avid high altitude climber. So he took this photo and he said, use it in your next seminar. And this was the next seminar, so I am using it here. So these are the places have been associated with IISc, UPS, Rishihood recently. It's a nice upcoming university in Sonipat, just outside Delhi. The IIT Mandi connection is very nice because I am associated there with a department called IKSHMA, which is called, I'll forget the name, Indian Knowledge Systems Mental Health Association Department or something. Now the mental health part, the subtitle of that is Musicology and Musopathy. That is, when you hear a particular piece of music, does it calm you down to the extent that you don't need Prozac and all those things? And they are doing scientific tests to figure out whether it has a soothing effect. And believe it or not, see, now I am there in that place. So throughout my life I have been wondering why the gatekeepers have kept me out of selection committees to choose IIT professors. I am sitting on a selection committee choosing music professors today. That's what has happened to me. And I have been asking them questions, Arunan, about pre-Sangam music and all that. Sometimes they answer, sometimes they don't answer. So finally I can say even I have appointed an IIT professor. So you see, life is long, it's very strange. वो भी IIT है, ये भी IIT है. और मैं selection committee में था. So you can't really predict the future, you can't predict crystal structures. And that's why we do science. We don't do science to do, if something is predicted, there is an MSc project, it's not PhD in science. Drishya Rahita, I said, the earlier simpler one is Adrishya, what you can't see. When you go there and you can't see it and you try to see it. That's what we do. And I hope that you have learnt a few things, or I learn, teachers and students, we learn from each other. Teacher is a student, student is a teacher, it's all mixed up. It's very nice that it gets mixed up like that. Because only then you can go forward and not regress somewhere. So thank you all once again. Couple of these books are there outside. So those of you who care to buy this Bharat is there, I think. This weak hydrogen bond you can't buy because the Amazon price is so high that I don't think anybody can afford to buy it. It's 84,000 rupees. So if anybody wants to buy it for 84,000, I will sell it. But I just brought it for fun. Because one fellow from Croatia told me that it had been read so much in his lab that the covers fell off the book. So I said, okay. So this is that blue book which is there, and then some other books. So if you all want anything, buy it. If you all don't want, don't buy. If anybody wants to learn more about Muthuswami Dikshitar and why it is relevant to IKS, it's here. Thank you all very much for listening to me. And if you all understood that vegetable and that fruit fellow, then I think at least half the audience, I think I communicated something at least. So it is a complex system. Research is difficult, let me tell you that. Research is not easy. By working hard, all you do is develop your capacity to do something. What gives you the capabilities, only the good Lord knows. I don't know. So if you feel you have the capabilities, then work on capacity building. Then only sky will be the limit for you. Thank you very much, all of you, and I'm very happy to be here today.
Very, very inspiring. Really delighted to have you and have listened to your lecture.
Thank you. Thank you very much. Thank you very much indeed. Thank you, all of you. Thank you. Thank you. Thank you indeed. Thank you. Romba thanks, Subha. Thank you for your good intro.
Yeah. Good evening, everyone. As we conclude this insightful event, it is my great privilege to propose a formal vote of thanks to everyone who has made this endowment lecture a resounding success. So we are grateful to our distinguished speaker, Professor Desiraju, for delivering such an enlightening lecture, and it's very crystal clear. Thank you for sharing your expertise and time with us today. And also we would like to thank Professor S. Chandrasekaran for presiding over today's event. A special note of appreciation goes to the visionary donors who made this endowment possible. We particularly acknowledge Professor Nambutri, Professor H.S.P. Rao, and the family members of Professor S.N.B., and the many colleagues whose collective generosity has established this lasting legacy in honor of academic excellence. We also extend our thanks to the Office of the Development and Alumni Affairs at IISc for their meticulous administration of the endowment funds. And I also would like to thank the chairman of the department, faculty colleagues, students of the department and the division for your active participation. Our appreciation also goes to the department staff. Their seamless coordination behind the scenes ensured that everything ran according to plan. Finally, I would like to thank our service providers for their essential contribution, Mr. Haridasan for his professional photography, and Mr. Fasa for the catering. And thank you all once again, and I wish you a pleasant evening ahead, and please join us for IT outside. Thank you very much.